Assalamualaikum. I am Nurul Dawisha binti Faris along with my teammates who is Nurul Najwa Akila Abdul Rahman, Nurul Ashikin Muhammad Mustafa Kamal, Nurul Afifah Abdul Aziz, also Nurul Nisa Asila Omar represents Group 3 will present to you about our Chemical Engineering Lab 2 project which is titled as Activated Carbon Absorption Isotherm and Kinetics in Removal of Dyes in Textile Industry. In this project, it consists two main objectives, which is first to study the effects of initial dye concentration, contact time, agitation speed, pH, and temperature on the absorption. And the second objective is to find the best fit isotherm for absorption process. Moving on to the next point, I will explain to you about market analysis for our project. The global water treatment chemical size was estimated at USD 28.9 billion in 2019 and is expected to grow at a compound annual growth rate of 3.2% from 2020 to 2030. Due to growing utilization in industrial settings for cooling, product formulations, rinsing, or even human consumption, if properly purified, raw water treatment emerged as the largest application segment with a revenue share of more than 45% in 2019. The wastewater treatment service market has been segmented by end-use industry into chemical, pharmaceutical, oil and gas, food, pulp and paper, metal and mining, and power generation, among others. The revenue growth in the global wastewater treatment service market is expected to be the highest in the power generation segment. Worldwide, there is a high demand for wastewater treatment services in the power generation industry. In most cases, residential wastewater is treated at a municipal wastewater treatment plant. In 2018, the municipal segment held the largest share of the total wastewater treatment services market. Global population growth has increased the demand for treated water. Water scarcity has increased the demand for more wastewater treatment and water recycling services, thereby expanding the wastewater treatment services market. As we can see in the graph, the municipal has the highest share in the global water treatment chemicals market share, followed by power and oil and gas.
Thank you, Darwisha. Hello, my name is Ashikin, and I'll be discussing about the process flow diagram for the wastewater treatment plant in textile industry. Firstly, wastewater effluent from the textile industry is flowed into the first unit operation, which is an equalization tank. In this tank, the high pH of textile industry effluents that caused due to significant amount of hydrolyzed alkaline dyes is adjusted by adding a suitable amount of hydrochloric acid. This is because the high pH of effluent will inhibit the growth of microbial. After that, the effluent is pumped into another tank for the aerobic process to take place, where a specific microbial culture is added for the process. Next, the effluent is transported into two clarifiers. The first clarifier is used to settle the solid particles and to adjust the pH, since the microbial activity may affect the pH of the effluent, while the second clarifier is used to coagulate and flocculate the effluent. Then, the effluent is fed through the activated carbon filter, where an activated carbon bed is used to absorb the color and odor. After that, the effluent from ACF is ozonated, where ozonator tanks are needed to provide the required dosage of ozone. Lastly, the effluent is treated by using the combination of ultrafiltration UF and reverse osmosis RO, where the effluent is initially treated in the ultrafiltration system and the reject from this ultrafiltration membrane is returned to the equalization tank. The effluent is then treated in the reverse osmosis process, with roughly half of the permeate from this process is kept in a storage tank before it being transported back to the textile industry to be reused. So that's all from me. Next, I'll pass the floor to Najwa and Afifah to discuss about the result and discussion.
Okay, for the results part, the first one is the effect of the contact time and initial concentration on the dye removal. Okay, from the graph obtained, the percentage of the dye removal increased with the increment of the initial concentration of the dye. This is because the initial of the concentration of the dye mostly influenced by the direct contact between the surfaces site on the adsorbents and the dye concentration. The second effect is the effect of pH on the dye removal. The percent of the dye remover raising up to pH 7 before gradually slowing down. The impact of the pH alteration at various levels on the dyes gives no influence on the absorbance or the wavelength. the reaction dye adsorption showing that the carbon has net positive charge on its surface. So when the charge increased, it led to a decrease in the pH of the adsorption solution. The third one is the effect of the temperature on the dye removal. From the results plot, the adsorption capacity decreased as the temperature increased. It is also caused the increment in the percentage of the dye removal because of the movement of the particles in the solution also increased.
Hi, I'm Najwa. To study the effect on agitation, the removal of dye was conducted at different agitation speeds, which are 610, 800, and 1000 rotation per minute within 90 minutes while keeping other parameters constant. Based on the graph given, it can be seen that as the agitation speed increases from 610 rpm to 1000 rpm, the percentage of dye removal also increases from 78% to 87% within the period of 90 minutes. The increment is due to the mass transfer of adsorbate to the internal surface of particle that influence the adsorption kinetics. At low agitation speeds, the film diffusions become the rate limiting step as the fluid film around the particle is thicker, causing the contact between adsorbent and adsorbate to be reduced. Meanwhile, the film diffusion increases to the maximum value at higher agitation speeds, causing the pore diffusion to become the rate controlling step due to the acts of centrifugal forces. However, some studies found that the adsorption increases only up to certain limit with the increment of agitation speed, which means there is no significant increase in the adsorption capacity. Therefore, we can conclude that the agitation speeds only affects the adsorption kinetics. To determine best free isotherm, the concentration of liquid and gas phase at equilibrium is used to construct the adsorption isotherm. Using the experimental data obtained and the constructed isotherm, it can be concluded that the Langmuir isotherm is the better representation of the adsorption process. This is because Kaolin particle exists as an anion, and the dye molecule exists as the cation in an aqueous solution. As the result, chemisorption occurs rather than the physical adsorption. Therefore, it is safe to assume that only a monolayer of dye molecule is covering the Kaolin surface. To further prove this, the Langmuir and Freundlich models are fitted and linearized to observe the correlation coefficients. Based on the table, it can be seen that the correlation coefficients of Langmuir is higher than the Freundlich model, which are 0.99 and 0.97 respectively. Hence, it is proven that the adsorption process of brilliant green dye by Kaolin obeys the Langmuir isotherm.
In this experiment, there are a few safety considerations that need to take note on. First, always wear protective gears when handling the chemical to minimize the exposure. Second, the unit must be operated under supervision of trained authorized staff. Third, all operating instructions must be read and understood before operate the unit. Next, inspect the unit or plant critically for any damage, leakage, and worn out. In the lab, all chemicals, dyes need to be recorded, clearly labeled, and properly handled. All the chemical waste must be disposed properly after each of experiment. And lastly, all safety precautions in laboratory and plant need to be observed. In conclusion, this experiment is related to experiment 9, activated carbon isotherm and kinetic, which adsorbate used in this experiment is brilliant green dyes, while adsorbent is kaolin. The objective of this experiment were achieved when the initial concentration, the pH of dye solution, and operation temperature were found to be significantly influence the adsorption capacity, while the agitation speed influenced the adsorption kinetics. And from the experiment, the adsorption experimental data obeys the Langmuir isotherm model. It also can be concluded that kaolin is an alternative adsorbent with high percentage of dye removal that can replace the activated carbon adsorbent in the textile wastewater treatment. That's all from our group. Thank you.